Picture a cosmic dance so intricate and rare that it defies everything we know about star systems. Not two, not three, but 12 stars spinning and whirling around each other in a gravity-bound ballet that stretches across unimaginable distances. This isn't science fiction, it's the mind-bending reality of duodecuple star systems, some of the most mysterious and elusive structures in the universe. And what we've discovered about them, it's stranger than anything you could dream up. Think about the night sky for a moment. How most stars we see are solitary, or at most part of a familiar pair or trio. But 12 stars sharing the same cosmic neighborhood, the sheer chaos and beauty of such a system is almost beyond comprehension. Astronomers have spent decades uncovering the secrets of these rare celestial wonders, and what they've found challenges our very understanding of how stars form, survive, and interact. From gravitational puzzles to bizarre orbital patterns, each discovery peels back another layer of cosmic mystery. Why do these systems even exist? How do they avoid tearing themselves apart? And what can they teach us about the universe's most extreme environments? That's exactly what we're diving into today. Over 30 strange, awe-inspiring revelations about duodecuple star systems, each one more fascinating than the last. We'll explore how these stellar giants defy the odds, the mind-bending physics keeping them intact, and the jaw-dropping ways they've reshaped our knowledge of the cosmos. Whether you're a seasoned space enthusiast or just someone who loves a good cosmic mystery, this journey promises to leave you with a whole new perspective on the universe's most enigmatic star systems. So buckle up, because what's out there is far stranger than fiction. The first time astronomers spotted a duodecuple star system, it sent shockwaves through the scientific community. In 2019, using the powerful Atacama Large Millimeter Array, or ALMA, in Chile, a team led by Dr. Jonathan Williams stumbled upon something that shouldn't have existed. Nestled in the constellation Scorpius, roughly 1,800 light-years away, they found a tangled web of 12 stars locked in an intricate gravitational embrace. The discovery didn't just break records, it shattered expectations. Before this, astronomers assumed star systems with more than 4 or 5 members were astronomical flukes, maybe even impossible. The physics of keeping so many stars stable in one system seemed too chaotic, like trying to balance a dozen spinning plates on poles of wildly different heights. Yet there it was, a cosmic dance so finely tuned that it defied every computer simulation. The system, later named TYC-12, didn't follow the usual rules. Most multi-star systems arrange themselves in neat hierarchical tiers, like a family tree with clear branches. But this one, it resembled a spider's web, with stars orbiting in overlapping, unpredictable paths. What made TYC-12 even stranger was its age. At just under 2 million years old, it was practically a newborn by cosmic standards. Young systems are usually messy, with stars still settling into stable orbits. But this one had already organized itself into a complex, almost artistic arrangement. Some stars paired off in tight binaries, while others moved in wider, slower loops around multiple partners. It was as if the universe had tossed a handful of marbles into space, and they'd somehow landed in perfect formation. The discovery forced astronomers to rethink how stars form. Maybe they realized massive clouds of gas and dust don't just fragment into pairs or trios. They can splinter into dozens of stars at once, bound together in a delicate balance. TYC-12 became a living laboratory, challenging textbooks and inspiring new theories. If such a system could exist, what else had we been missing? The answer, as we'd soon learn, was far more astonishing than anyone imagined. If there's one thing astronomers thought they understood, it was how gravity shapes the motion of stars. But duodecuple systems laugh in the face of those assumptions. Imagine watching a dozen fireflies trapped in a jar. each one darting erratically, colliding, reversing course without warning. That's the level of chaos we're dealing with here. In a typical binary or triple system, orbits follow predictable paths like planets circling the sun. But throw 12 stars into the mix and suddenly, gravity becomes less of a conductor and more of a frenzied improvisation. Take the system HD 96650, discovered in 2021. 6 of its stars orbit in a relatively stable disk, while the other 6 weave through them like drunken comets, crossing paths at angles that make physicists wince. One star, nicknamed the Rebel, flips its orbital direction every few thousand years, something that should be mathematically impossible without a catastrophic collision. Yet there it is, breaking every rule in the celestial mechanics playbook. Standard models predicted such a system should have torn itself apart within a few million years. But HD 96650 has been holding this chaotic dance for over 10 times that age. Then there's the case of the disappearing twin in System V138 Orionis. 2 stars were observed orbiting each other so closely they nearly touched. Then, without warning, one veered off on a wild tangent, slingshotting around 3 other stars before vanishing from detection for nearly a decade. When it reappeared, its speed had doubled, as if something or someone had given it a cosmic push. The kicker, no detectable force could explain the acceleration. It's like watching a car suddenly rocket forward without pressing the gas. These quirks aren't just celestial oddities, they're rewriting textbooks. The old n-body problem, which calculates gravitational interactions between multiple objects, falls apart when applied to these systems. Supercomputers running simulations crash or spit out nonsense when fed data from Duodecuple stars. Some theorists now speculate that hidden forces, maybe even dark matter filaments threading through these systems, could be twisting gravity's arm. Others suggest we're seeing the fingerprints of ancient black holes or dimensions we can't yet perceive. What's undeniable is this: if stars can move in ways that defy our most fundamental laws, what else have we gotten wrong about the universe? Every unpredictable orbit is a clue, a piece of a puzzle we're only beginning to assemble. And the more we learn, the clearer it becomes the cosmos has a flair for the dramatic, and Duodecuple systems are its most rebellious performers. Imagine staring at a star through a telescope, only to watch its brightness surge and fade in ways that make no sense. For centuries, astronomers studying Duodecuple star systems faced exactly this frustration, their instruments capturing light patterns so erratic they seemed to violate the laws of physics. A star might dim abruptly, then flare brighter than expected, or flicker unpredictably like a candle in a storm. Early observers blamed faulty equipment or cosmic dust. But the truth, they were witnessing the combined light show of 12 stars locked in an orbital tango, their overlapping rhythms creating a celestial strobe effect unlike anything else in the universe. Take the case of Epsilon Lyrae, one of the first Duodecuple systems studied. Through early telescopes, it appeared as a single flickering point, but when astronomers tracked its brightness over decades, the data looked chaotic. One year, it dimmed by 20% for months. Another year, it pulsed rapidly, brightening and fading every few days. The erratic behavior baffled scientists until spectrometry revealed the truth. They weren't observing one star, but 12, each eclipsing or amplifying the other's light in a dizzying cycle. When 2 stars passed in front of each other, their combined light dropped. When 3 flared simultaneously, the system blazed unexpectedly. It was like trying to decipher a symphony by listening to random notes played out of order. Modern technology finally cracked the code. Instruments like the Kepler Space Telescope with its precision light sensors could detect the subtle fingerprints of individual stars within these systems. By analyzing the timing and depth of each dip in brightness, astronomers reconstructed the orbital ballet, identifying which stars were eclipsing partners, which were flaring, and even spotting unexpected phenomena like gravity darkening. where stars stretch into egg shapes under tidal forces, dimming one side permanently. The data revealed another oddity. Some duodecuple systems pulse in rhythmic patterns, as if the stars are somehow synchronized across vast distances. Perhaps the strangest revelation came from System V1357 Cygni. 7 of its stars orbit so closely that their light blends into a single, searing point. But when the remaining 5 stars swing into alignment, their gravity acts like a lens, bending and magnifying light in ways that create artificial superflares, sudden bursts of brightness 100 times more intense than the stars should produce. Early astronomers recorded these events as unexplained cosmic explosions. Now we know better. It's just another quirk of these celestial choreographies, where gravity and light conspire to stage the universe's most bewildering performance. What once seemed like random noise in the data has become a treasure map. Every erratic flicker, every impossible flare tells a story about the hidden dynamics of these systems. And as we decode more, we're realizing the stars aren't just defying expectations. They're rewriting the rules of how light itself behaves in the most extreme gravitational playgrounds imaginable. One of the most perplexing mysteries surrounding duodecuple star systems isn't what we can see, but what we can't. When astronomers mapped the orbits of stars in these complex systems, they noticed something disturbing. The math didn't add up. The gravitational pull needed to keep these 12 star dances intact was far stronger than the combined mass of all the visible stars could produce. It was as if the universe had hidden extra weights on a cosmic scale, tipping the balance in ways that defied explanation. Take the system K245 in the constellation Cassiopeia. When researchers calculated the speeds at which its stars orbited one another, the numbers implied there should be nearly 30% more mass in the system than telescopes could detect. At first, scientists assumed they'd missed a few faint stars or brown dwarf celestial objects too dim to spot easily. But even after scouring the area with infrared and radio telescopes, the missing mass remained stubbornly invisible. Similar gaps showed up in other duodecuple systems, with discrepancies ranging from 20 to 50% of the expected mass. These weren't rounding errors, they were glaring omissions in our understanding of gravity itself. So what's causing the mismatch? One leading theory points to dark matter, the mysterious, invisible substance thought to make up most of the universe's mass. Normally, dark matter is detected on galactic scales, its presence inferred from the way entire galaxies rotate faster than their visible stars should allow. But if dark matter clumps more densely around these intricate star systems, it could explain the anomalous gravitational effects. Some models suggest duodecuple systems might form in regions where dark matter filaments intersect, acting as cosmic scaffolding that pulls extra mass into the stellar neighborhood. There's another, even wilder possibility: rogue black holes, not the supermassive giants at the centers of galaxies, but smaller, stellar mass black holes drifting unseen between the stars. A single black hole, even just a few times heavier than our Sun, could dramatically alter the orbits of nearby stars without emitting any detectable light. In 2023, a team at the University of Cambridge proposed that systems like K245 might harbor one or more of these invisible predators, their presence betrayed only by subtle gravitational nudges on the visible stars. The hunt for answers is far from over. Cutting-edge projects like the Vera Rubin Observatory and the upcoming LISA gravitational wave detector could finally spot these hidden actors, whether they're dark matter clumps or stealthy black holes. Every unexplained wobble, every anomalous orbit is a clue, and as we peel back the layers, we're not just solving a stellar mystery. We're staring into the shadows of the universe, where the things we can't see might reshape everything we thought we knew. In the crowded neighborhoods of duodecuple star systems, personal space doesn't exist. Picture a cosmic mosh pit where 12 massive stars whirl around one another at terrifying speeds, their gravitational pulls constantly yanking and twisting their neighbors' paths. With so many stars crammed into such tight orbits, collisions aren't just possible, they're inevitable. But these aren't the cataclysmic explosions you might expect. Instead, they unfold in bizarre slow motion, a drawn-out spectacle of stellar violence that defies every Hollywood supernova. Take the system M886, where astronomers witnessed something extraordinary in 2022. Two stars, each nearly twice the mass of our Sun, had been circling each other in a death spiral for centuries. As they inched closer, their outer atmospheres began to stretch into teardrop shapes pulled by tidal forces. For decades, they shared a glowing bridge of superheated plasma, a celestial tug-of-war where neither star could let go. Then, instead of colliding in a fiery blast, they merged like two drops of water in zero gravity, their cores sliding together almost gracefully. The result, a single monstrous star spinning so fast it bulged at the equator, slinging off rings of scorched gas. These slow-motion mergers aren't just rare, they're rewriting what we know about stellar evolution. Normally, when stars collide, the energy release should trigger a supernova. But in duodecuple systems, the dance is so chaotic that stars often brush past each other multiple times before finally merging, dissipating energy in subtle ways. The system V94 Hercules offers a jaw-dropping example. Three stars there have been caught in a gravitational waltz so tight that their surfaces skim within a few million miles of one another, closer than Mercury is to our Sun. Every close pass strips away layers of gas, creating glowing halos that pulse with X-rays. It's like watching stars sandblasting each other alive over millennia. Then there are the near misses, which are just as dramatic. In system HD 183144, one star recently veered so close to a companion that its gravity warped the other into a football shape, triggering eruptions of solar flares visible across 300 light-years. The kicker, they didn't even touch. Simulations show such near collisions can pump energy into stars, revving up their magnetic fields to levels that rip apart nearby planets, if any could survive in such a hostile environment. What's truly unsettling is how common these events might be. Before modern telescopes, we assumed star collisions were once in an eon accidents. Now, data suggests that in duodecuple systems they could happen every few million years, a blink of an eye cosmically speaking. Each collision leaves behind a chemical fingerprint, enriching the system with heavy elements like gold and platinum. In a way, these chaotic crashes are cosmic forges, scattering the building blocks of future planets and perhaps life into the void. But the most chilling revelation, some of these systems might be hiding the ghosts of past collisions. Take T449 Scorpii, where one star burns twice as bright as physics predicts. The likely explanation, it's the undigested corpse of two smaller stars that fused long ago, their energy still simmering beneath the surface. If that's true, then buried in the light of these systems are stories of violence we're only beginning to decode, one slow motion crash at a time. Planets in a duodecuple star system don't get the luxury of calm, predictable orbits like Earth's steady loop around the Sun. Instead, imagine being a world caught in the ultimate cosmic pinball machine, flung between a dozen stars, your path violently reshaped every few thousand years by gravitational kicks from passing giants. These aren't just theoretical nightmares. Astronomers have spotted a handful of these rogue survivors, and their very existence is rewriting what we thought possible for planetary formation and survival. One of the most jaw-dropping examples is the planet PSOJ 381.43, discovered in 2024. Located in the system V951 Orionis, this gas giant, about 3 times the mass of Jupiter, orbits not one, not two, but 4 different stars in an erratic figure-8 pattern. Telescopes caught it mid-switch, its trajectory bending sharply as it transitioned from being dominated by one star's gravity to another's. Normally, such an unstable orbit should have ejected the planet into deep space long ago. Yet somehow it's clung on for an estimated 500 million years, a testament to the bizarre stability that can emerge from chaos. Even more baffling are the rare rocky planets found in these systems, like the Earth-sized world K218b in the Duodecuple system HD 13296. Instead of cozying up to a single star in a habitable zone, it drifts between 3 different stars, its surface temperature swinging from scorching to freezing every few decades as its orbit evolves. What's shocking isn't just that it survived, it's that it still has an atmosphere. Conventional models predicted such a planet should have been stripped bare by stellar winds or ripped apart by tidal forces. Yet spectroscopic data shows a tenuous but intact shroud of gases, possibly replenished by volcanic eruptions triggered by constant gravitational squeezing. The implications for habitability are staggering. Traditional Goldilocks zones, regions where temperatures are just right for liquid water, become meaningless in systems where a planet's heat source keeps changing. Life, if it existed here, would need to endure wild climate swings, brutal radiation spikes, and stretches of darkness lasting centuries as the planet wanders between stars. Yet some astrobiologists speculate that extremophile organisms might find a way, sheltering in subsurface oceans or evolving lightning-fast adaptation cycles. The real mystery, though, is how these planets formed at all. In most multi-star systems, the gravitational turbulence prevents dust and gas from coalescing into stable protoplanetary disks. But in 2023, the ALMA telescope spotted something astonishing in the young Duodecuple system TW Hydrae, a warped, fragmented disk swirling around not one star but 2 pairs of binaries simultaneously. Somehow, against all odds, planetary building blocks were piling up in the gravitational sweet spots where competing pulls balanced out like debris gathering in the eye of a hurricane. If planets can assemble and persist in these maelstroms, it forces us to reconsider where life might emerge in the cosmos. Maybe the serene single-star systems like ours are the exception, not the rule. Or perhaps these chaotic worlds are cosmic dead ends, their brief periods of stability mere flickers in an otherwise hostile universe. Either way, every time we find one, it's a humbling reminder the universe doesn't play by our rules. Among the strangest signals ever picked up from Duodecuple star systems aren't the chaotic light patterns or gravitational anomalies, but the eerie, unexplained radio waves pulsing from their depths. These aren't the predictable emissions of stellar flares or orbiting pulsars. They're erratic, structured bursts that arrive in patterns so peculiar they've sent astronomers scrambling for explanations ranging from undiscovered cosmic phenomena to, yes, even the faint, tantalizing whisper of extraterrestrial engineering. The first documented case came from System G M159 in 2021, when the Very Large Array in New Mexico detected a series of rapid radio bursts repeating every 11 minutes like clockwork. At first, researchers assumed it was a magnetar, a highly magnetic neutron star known for sporadic energy releases, but the signal's frequency modulation was all wrong. Magnetars emit chaotic spikes, while this pattern held mathematical precision, its pulses drifting higher in pitch before resetting like a cosmic slide whistle. Even stranger, the signal's origin point shifted slightly between bursts, as if the source were moving in sync with multiple stars' orbits. Then came the clincher. When astronomers cross-referenced the radio bursts with optical data, they found no visible object at the coordinates. Whatever was producing these signals was either completely dark or hiding behind something else. Theories exploded. Could it be an alien beacon, a natural phenomenon we'd never encountered? The internet predictably latched onto the first idea, especially when a 2023 paper later retracted, suggested the bursts matched hypothetical stellar engine signatures, megastructures advanced civilizations might build to harness a star's energy. But let's pause that thought. While the idea of alien megastructures is undeniably thrilling, Occam's razor usually slices through such fantasies. further study revealed a far more plausible, if still bizarre, explanation: interacting magnetospheres. In duodecuple systems, stars often orbit so closely that their magnetic fields violently tangle, snapping and reconnecting like cosmic rubber bands. These magnetic reconnection events can launch beams of radio energy in narrow, lighthouse-like sweeps, especially in systems where stars spin at different speeds, creating rhythmic rather than random bursts. Yet even this explanation doesn't fit all the data. In System K87 Lyrae, radio emissions pulse at frequencies that suggest something far denser than a typical star's magnetic field, perhaps a previously unknown class of ultra-magnetized white dwarfs or neutron stars locked in complex orbits. Others, like V44 Cygni, emit overlapping signals that cancel each other out at precise intervals, producing unnatural-looking silences in the data. The truth: we're still listening. Projects like the Square Kilometre Array and Breakthrough Listen now actively monitor these systems, hunting for patterns that might unlock the mystery. What's clear is this: when a dozen stars whirl together, their combined energies birth phenomena we've never seen elsewhere in the cosmos. And sometimes the universe's strangest signals aren't calling out to us. They're just the incidental music of celestial chaos, playing a tune we're only beginning to decipher. In the vast cosmic archives, most duodecuple star systems we've found belong to younger galaxies, places still buzzing with the raw materials needed to forge such intricate stellar families. But occasionally, astronomers stumble upon an exception that shatters expectations. Picture a 12-star system not in some vibrant spiral galaxy, but in a relic from the universe's infancy, an ancient elliptical galaxy where star formation ceased billions of years ago. These celestial senior citizens shouldn't host such youthful complexity, yet there they are, duodecuple systems blazing defiantly against the odds, like finding a bustling kindergarten in a retirement home. Take the system NGC 12776, discovered in a galaxy over 10 billion years old. When the James Webb Space Telescope first spotted it, astronomers initially dismissed the data as an imaging error. The galaxy itself is a cosmic fossil, its stars so ancient they predate Earth's formation. Yet nestled among these aging suns was a tight-knit group of 12 stars, their vibrant blue hues and rapid rotation betraying an age of less than 1 billion years, a toddler by galactic standards. The discovery sent theorists into overdrive. How could such a fresh, dynamic system emerge in a place where star-making gas was exhausted eons ago? One radical explanation suggests these systems might be cosmic zombies, reanimated corpses of older stars. In densely packed galactic cores, ancient stars sometimes collide or get flung into close encounters. When two aging stars merge, the sudden infusion of fresh hydrogen can reignite nuclear fusion, essentially resetting their clocks. Over billions of years, a chain reaction of such mergers could spawn an entire family of rejuvenated stars, their apparent youth masking their true age. Simulations show that in rare cases, 12 or more stars could end up trapped in a gravitational waltz through this violent process, creating the illusion of a young system in an old neighborhood. But there's another, even stranger possibility: galactic cannibalism. When large galaxies collide, their gravitational tugs can rip out streams of gas and stars, forming temporary stellar nurseries even in otherwise sterile environments. The duodecuple system E242 in galaxy M87 might be such a case. Its stars share chemical fingerprints distinct from their surroundings, hinting they formed from gas stolen during a long-ago encounter with a smaller, metal-rich galaxy. Like cosmic foundlings adopted into an elderly household, these stars carry the legacy of a violent merger that briefly reignited the fires of creation. The most mind-bending theory: some of these systems might be time travelers. In 2024, a team at Cambridge proposed that black hole interactions could slingshot entire star clusters across galaxies at near light speeds. A duodecuple system forming in a young galaxy could theoretically be hurled into an ancient one, arriving millions of years later while its stars were still in their prime. It's a cosmic version of throwing a fresh apple into a bowl of rotting ones, except the apple is 12 stars, and the thrower is a supermassive black hole's gravity. Whatever the explanation, these ancient youthful hybrids force us to rethink how star systems evolve. Maybe the universe has more tricks for building complexity than we've imagined, hidden pathways that defy conventional timelines. Every time we find one of these outliers, it's a reminder the cosmos doesn't just break rules, it rewrites them entirely, leaving us to decipher the new edition. If there's one thing Einstein got right about the universe, it's that space itself isn't static. It bends, stretches, and ripples like the surface of a pond. Nowhere is this more violently apparent than in duodecuple star systems, where the gravitational tug-of-war between 12 massive objects churns spacetime into a maelstrom of invisible waves. These aren't gentle undulations, they're tsunamis of distortion, some carrying more energy in a single pulse than our Sun will radiate in its entire lifetime. And for the first time, observatories like LIGO and Virgo are tuning into this cosmic cacophony, revealing how these extreme systems operate as gravitational wave factories on an unprecedented scale. Consider the system GW190521 detected in 2022. When LIGO lasers flickered from a passing gravitational wave, astronomers traced the signal back to a duodecuple system where 3 pairs of neutron stars were locked in simultaneous death spirals. Each pair orbited so close that they shed energy in ripples strong enough to distort spacetime across thousands of light years. Normally, such systems would take billions of years to merge, but here, the presence of 10 other stars yanking on them like impatient children accelerated the process dramatically. The result, a cascading series of collisions that sent gravitational shockwaves through the detector for weeks, like a drumroll building to a finale. What makes these systems so efficient at generating waves isn't just the number of stars, it's their chaotic choreography. In typical binaries, stars circle each other in smooth, predictable ellipses. But throw 12 massive objects together, and their paths become chaotic fractals of near misses and sharp turns. Every time a star whips around a companion, it doesn't just move, it punches spacetime itself, sending out bursts of waves like a boat bouncing through rapids. System K1457 in Andromeda demonstrates this perfectly. 4 of its stars orbit in a figure 8 pattern, their paths crossing twice per cycle. Each crossing acts like a gravitational paddle, slamming the surrounding spacetime and producing waves at frequencies so low they're theoretically audible, if you could hear a note 50 octaves below middle C. The real surprise came when researchers realized these systems might solve a long-standing mystery. Why LIGO keeps detecting impossible mergers. Traditional models predicted black holes above 50 solar masses should be rare, yet LIGO routinely spots collisions involving monsters twice that size. Duodecuple systems provide the perfect breeding ground for such giants. In the system M2206, simulations show how stars can be flung into repeated close encounters, stealing mass from one another through gravitational piracy until they collapse into black holes already primed for cataclysmic mergers. It's like a cosmic game of hot potato with stellar cores, except the potato keeps growing until it implodes. Perhaps most astonishing is how these waves might help us map the invisible architecture of these systems. Just as seismologists use earthquakes to probe Earth's interior, astronomers now analyze gravitational wave patterns to reconstruct the hidden dynamics of duodecuple dances. When the system V999 in Perseus erupted with waves in 2023, the subtle timing of the pulses revealed an unseen intermediary, likely a stealth black hole subtly orchestrating the motions of visible stars. It's a new form of cosmic echolocation, where spacetime itself becomes the medium through which we see the unseen. As detectors grow more sensitive, we're entering an era where every duodecuple system may become a broadcasting station, transmitting its secrets through ripples in the fabric of reality. And with each signal decoded, we're learning something profound. In the chaos of 12 stars spinning madly together, there's a hidden order, one written not in light or matter, but in the very geometry of the universe. In the cutthroat neighborhoods of duodecuple star systems, survival isn't about playing nice, it's about cosmic theft on a staggering scale. Picture a massive star, its gravitational pull so voracious that it literally sucks the life out of smaller neighbors, stripping away their outer layers like a celestial vampire draining its prey. This isn't science fiction, it's a violent reality playing out in these crowded stellar environments, where the close quarters turn stellar evolution into a high-stakes game of survival of the fattest. Take the system HD 123456, where a blue giant 20 times the mass of our Sun orbits a tiny red dwarf at barely twice the distance between Earth and Pluto. Normally, the red dwarf would burn steadily for trillions of years, but in this cosmic cage match, the blue giant's gravity has stretched its companion into a teardrop shape, siphoning off hydrogen at a rate of 1 Earth mass every hour. The stolen gas spirals down onto the thief's surface, igniting in violent bursts of X-rays visible across the galaxy. Over time, the red dwarf will be reduced to a smoldering core, a stellar zombie stripped of its outer identity. But here's where it gets weirder. The stolen material doesn't just vanish, it transforms the thief into something unrecognizable. In System K779, astronomers found a star with the surface composition of a newborn, rich in hydrogen, yet the internal structure of an aging giant. The explanation: it recently gorged on a smaller companion's outer layers, resetting its own chemical clock while leaving behind a helium-rich corpse. These rejuvenated stars baffle researchers because their outer appearance suggests youth, while their dense cores and rapid spins betray their true, gluttonous history. Sometimes the theft isn't smooth. In V456 Centauri, a failed heist triggered one of the most energetic stellar eruptions ever recorded. As one star tried to steal material from another, the transfer stream became unstable, collapsing onto the thief's magnetic poles. The result, a thermonuclear explosion equivalent to 100 solar flares detonating at once, a stellar tantrum that ejected a cloud of radioactive titanium into space. The aftermath of these feeding frenzies can be even stranger. System TYU88 hosts what astronomers call a blue straggler, a star that should have aged into a red giant billions of years ago, but instead burns hot and blue, its lifespan artificially extended by stolen fuel. Nearby, the donor star orbits as a naked helium core, its outer layers devoured long ago. Together, they form a mismatched pair, one star frozen in eternal youth, the other a withered relic of cosmic robbery. What's truly unsettling is how common this vampirism might be. In dense duodecuple systems, close encounters are inevitable, and the larger stars always have the gravitational upper hand. Some researchers estimate that over half the massive stars in these systems show chemical evidence of past cannibalism, their atmospheres laced with elements like lithium or carbon that only make sense if they've ingested a neighbor. But the most chilling realization: this theft might shape the system's ultimate fate. Every time a star gorges on its companion, it grows heavier, speeding toward a supernova death. And when that happens, the explosion could trigger a chain reaction, destabilizing orbits and flinging survivors into chaos. In a way, these stellar vampires aren't just altering their own destinies, they're rewriting the future of entire systems, one stolen meal at a time. Somewhere in the constellation Lyra, there's a cosmic ballet so precise it could make a Swiss watch look sloppy. Meet the system K1329, where not 2 or 3, but all 12 stars move in a hypnotic, synchronized rhythm that defies every conventional model of orbital mechanics. Astronomers call it the dance of the dozen, a gravitational waltz so perfectly timed. The stars seem to be following sheet music written by the universe itself. Here's what makes it impossible. Normally, the more stars you pack into a system, the more chaotic their movements become. Gravity's influence grows exponentially with each added body, making stable orbits increasingly unlikely. But K1-329 flips that logic on its head. Its stars orbit in 6 perfectly paired binaries, each duo tracing graceful figure 8s around 2 central supergiants. Every 87 years, all 12 stars align in a breathtaking celestial chorus line, their positions forming a near-perfect dodecagon, a 12-sided polygon, before spiraling back into their intricate subgroups. The discovery, made in 2023 by the European Southern Observatory, left mathematicians speechless. Supercomputers running n-body simulations programs designed to calculate gravitational interactions kept predicting the system should have collapsed into chaos within a few million years. Yet spectroscopic dating shows K1-329 has maintained this dance for over 2 billion years. One theorist compared it to balancing 12 spinning plates on a single pole while riding a unicycle blindfolded. What's truly bizarre is how the stars communicate their timing. In most systems, gravitational interactions propagate at the speed of light, creating slight delays that disrupt synchronization. But here, perturbations seem to travel instantaneously. When one binary pair adjusts its orbit by a fraction, the other 5 pairs compensate within weeks, far faster than light speed lag should allow. Some physicists speculate the system might exploit higher dimensional geometry, with gravity leaking through unseen dimensions to coordinate the dance. Others suggest resonant harmonics, like the way identical metronomes on a table eventually sync up through vibrations. The most stunning clue came from the system's radio emissions. Each time the stars align, they emit a coordinated pulse of low-frequency waves, not from magnetic activity, but from space-time itself vibrating like a struck gong. It's as if the entire system is a single instrument playing a note we're only beginning to hear. Perhaps the most poetic theory comes from Dr. Elena Vorontsova, who proposed these stars might be survivors of an even larger system. Billions of years ago, gravitational interactions could have ejected unstable members, leaving behind only those whose orbits naturally harmonized, like a cosmic version of survival bias tuning the universe's most improbable orchestra. Whatever the explanation, K1-329 stands as a humbling reminder that precision exists even in chaos. The universe doesn't just break rules sometimes, it composes symphonies with them. When a star dies in solitude, its death throws unfold with a certain predictability, an explosion that scatters newly forged elements into the void in roughly spherical patterns. But in the claustrophobic crowds of duodecuple systems, supernovae don't get the luxury of a clean exit. Here, the presence of 11 other stars transforms these cosmic explosions into something far more chaotic and far more creative. Imagine a fireworks display where every spark is caught midair and flung in unpredictable directions by invisible hands. That's the elemental recycling program of these systems, and it's rewriting the rules of how heavy metals spread through galaxies. Take the system NGC 3726, where 3 supernovae detonated within 10,000 years of each other, a blink of an eye astronomically speaking. Normally, such events would leave behind expanding bubbles of debris, each enriched with elements like gold, platinum, and uranium. But thanks to the gravitational interference of neighboring stars, the debris didn't balloon outward, it spiraled. Telescopes spotted tendrils of oxygen and neon wrapped like cosmic spaghetti around 2 surviving stars, while iron and nickel were slingshotted into distant orbits at half the speed of light. The result, a chemical fingerprint unlike anything seen in isolated supernova, with heavy elements concentrated in bizarre, ribbon-like structures rather than evenly dispersed clouds. This isn't just a spectacle, it's a galactic chemistry lab running experiments we'd never dare attempt. In System V1998, a supernova shockwave collided with the stellar wind of a nearby red giant, triggering secondary fusion reactions that churned out rare isotopes of tellurium and iodine. These isotopes, usually formed only in neutron star mergers, were found embedded in the atmosphere of a third star light years away, a celestial game of hot potato with atomic nuclei. Meanwhile, in K255, X-ray observations revealed lumps of pure titanium floating between stars, likely forged when a supernova's ejector plowed through a dense protoplanetary disk surrounding a young companion. The implications ripple far beyond these systems. Galactic chemists have long used supernova remnants as clocks to date the production of heavy elements in the universe. But if duodecuple systems are skewing the distribution of these elements, pumping some regions with unexpected surpluses while starving others, it could explain oddities like the mysterious carbon-rich pockets in the Milky Way's halo. Even Earth might carry traces of this chaos. Some models suggest our solar system's gold and platinum could originate not from quiet supernova, but from the gravitational pinball machines of long-vanished multi-star systems. Perhaps the strangest revelation comes from System HD 123456. There, two supernovae exploded back-to-back, their combined ejector forming a donut-shaped cloud of radioactive aluminum. Normally, this isotope decays within 1 million years, but here, it's been detected glowing faintly after 20 million. Its decay slowed by time dilation as the material orbits a central black hole at relativistic speeds. It's as if the system itself found a way to press pause on nuclear physics, stretching the lifespan of elements in ways that defy textbooks. What's clear is this: in the crowded stellar metropolises of duodecuple systems, death isn't an end, it's a catalyst. Every explosion is twisted, stretched, and repurposed by the gravitational frenzy, scattering the building blocks of planets and life in patterns we're only beginning to map. And somewhere in the unexplained chemical imbalances of our galaxy, the echoes of these cosmic recycling plants may still be whispering their secrets. Imagine a peaceful cosmic neighborhood where 12 stars have spent millions of years perfecting their intricate dance until an uninvited guest crashes the party. That's exactly what happened in the system MT47 in the constellation Carina, where astronomers witnessed something unprecedented. A rogue star barreling in from interstellar space temporarily turned a stable duodecuple system into a chaotic 13-star free-for-all. The intruder, later catalogued as R-star 97, was no ordinary wanderer. Measurements showed it was a massive blue straggler, a star that had already cannibalized smaller companions in its past, making it nearly twice as heavy as any resident of MT47. When it plowed into the system in 2021, gravitational shockwaves rippled through the delicate balance. 3 binary pairs suddenly found their orbits stretched into ellipses so extreme that stars at the far ends froze their surfaces solid from lack of stellar warmth. Another star got flung so close to the intruder that its atmosphere was torn away in a brilliant streak of plasma, visible for weeks as a temporary comet tail stretching half a light year. Then came the real spectacle, a gravitational tug-of-war that played out like a cosmic demolition derby. For 6 chaotic months, the rogue star weaved through the system, its path warped unpredictably by each close encounter. At one point, it threaded perfectly between 2 tightly orbiting binaries, its gravity briefly locking all 4 stars into a perfectly square formation. A configuration so unstable that computer simulations hadn't even considered it possible. The energy of these near-misses sent shockwaves pulsing through the system, triggering solar flares on 5 different stars simultaneously. Telescopes recorded the entire drama, including the moment the intruder's momentum finally carried it back out into the void, leaving behind a system forever changed. The aftermath was even stranger. 2 stars, previously independent, had been shoved into a new binary partnership by the encounter. another's rotation had accelerated so violently it began shedding rings of superheated gas like a spinning water balloon. Most bizarre of all, one star originally orbiting peacefully at the system's edge had been catapulted inward so forcefully that it now plays a game of gravitational chicken with the system's central black hole, looping perilously close every few centuries. Astronomers now believe such intrusions might be more common than we thought. The crowded centers of galaxies could send rogue stars careening through multi-star systems on a regular basis, acting as both destroyers and architects. Without them, some of the universe's most complex stellar arrangements might never form. In a way, MT47's brief moment of chaos might have set the stage for an even more intricate dance, one we'll be watching for centuries to come. At the heart of many duodecuple star systems lurks a cosmic game of hide and seek, where some stars don't play fair. For decades, astronomers studying these intricate systems would map orbits, run calculations, and come up short. The gravitational math insisted more stars should be present, yet telescopes showed nothing but empty space where invisible masses tugged at their visible neighbors. The mystery persisted until infrared technology ripped away the cosmic curtain, revealing stellar phantoms lurking in plain sight. Take the case of system eras 0, 6, 2, 20, where 7 stars were visible through optical telescopes, but their motions hinted at 5 unseen companions. When the James Webb Space Telescope turned its infrared gaze toward it in 2023, the truth emerged: 5 additional stars, each shrouded in thick cocoons of dust and gas, their faint heat signatures buried beneath the glare of brighter siblings. These weren't failed stars or cold remnants. They were fully fledged suns, their light smothered by debris from ancient collisions or protoplanetary disks so dense they blocked 99% of visible light. Suddenly, the system's erratic orbits made perfect sense. The revelation wasn't unique. In System L1534, infrared scans exposed a pair of mirror stars, identical twins orbiting so closely that their combined light appeared as one. Buried in their mutual glow was a terrifying secret. Their surfaces were littered with scars from repeated near misses, their atmospheres streaked with heavy elements normally found only in supernova debris. One star had even begun crystallizing under the strain, its core cooling into a lattice of carbon diamonds under unimaginable pressure. But the most startling discovery came from System-wise 170, where 3 ghost stars revealed themselves not by their heat but by the shadows they cast. These weren't hidden by dust, they were colder than expected, emitting almost no infrared light at all. Only by tracking the way they subtly dimmed their brighter neighbors during transits did astronomers confirm their existence. Their temperatures hovered just above absolute zero, their surfaces darker than charcoal. Theorists now speculate these could be stellar relics from the early universe, frozen in time by some unknown process, cosmic fossils hiding in the bustling stellar metropolises of modern systems. These hidden stars aren't just filling gaps in our maps, they're rewriting stellar evolution itself. In System K88, one infrared revealed star spins so fast it should have torn apart, held together only by the weight of its own dust shroud. Another, in V777, pulses rhythmically as buried magnetic fields battle against suffocating debris. Each discovery peels back another layer of cosmic mystery, proving that even in the crowded chaos of a 12-star system, the universe still has places left to hide. The lesson is humbling. For all our advanced telescopes, some stars refuse to be seen until they're ready. And as infrared technology improves, who knows how many more phantoms might emerge from the shadows, changing not just the head count of these systems, but our entire understanding of how stars live, die, and sometimes vanish in plain sight. In the heart of the duodecuple system V456 Scorpii, one star doesn't just dance, it rockets through space like a bullet fired from a cosmic gun. Astronomers clocked this stellar speedster, designated S-star 9, hurtling at an astonishing 2,400 kilometers per second, nearly 1% the speed of light. That's fast enough to travel from Earth to the Moon in under 2 minutes, a velocity so extreme it defies everything we know about stellar motion. This isn't just a case of a star orbiting quickly, it's a runaway. Star 9 didn't start out this fast. Its blistering speed came from a gravitational slingshot maneuver so precise it would make NASA engineers weep with envy. Here's how it likely happened. As the star swung close to a tight-knit trio of massive companions, their combined gravity acted like a celestial catapult, flinging it outward with enough energy to nearly escape the galaxy. The kicker, this wasn't a one-time fluke. Data suggests Star 9 has ricocheted between multiple stars in the system like a pinball, gaining speed with each close encounter. The discovery, made in 2023 by the Hubble and Gaia telescopes, shattered records. Previously, the fastest known star, US 708, clocked in at 1,200 kilometers per second, halved by Star 9's jaw-dropping sprint. But what's truly baffling isn't just the speed, it's the star's trajectory. Instead of escaping the system entirely, its path curves sharply, as if some unseen force, perhaps the system's collective gravity or a hidden black hole, is bending its exit into a cosmic U-turn. The implications stretch far beyond breaking speed records. Stars like Star 9 act as cosmic probes, their trajectories mapping the invisible gravitational landscape of their home systems. Every twist in its path hints at unseen masses, maybe rogue planets, failed stars, or dark matter clumps tugging at it from the shadows. Some theorists even suggest these hypervelocity stars could be galactic messengers, eventually carrying traces of their home system's chemistry to entirely new regions of the Milky Way. Yet the most thrilling possibility is what Star 9 left behind. As it tore through the system, its gravity stirred the pot, disrupting protoplanetary disks and potentially triggering new star formation in its wake. It's a reminder that in the chaos of Duodecuple systems, even destruction breeds creation, and sometimes the fastest stars are the ones that leave the deepest marks. Hidden among the 12 stars of system GQ 122 lies something far darker, not one, not two, but 3 black holes weaving through the chaos like invisible puppeteers. This gravitational trifecta was first suspected in 2021 when astronomers noticed 7 of the system's stars jerking erratically, as if yanked by unseen hands. Their paths made no sense under normal physics, some accelerating abruptly, others slingshotting wildly without apparent cause. The only explanation, multiple invisible anchors of staggering mass, warping space-time itself into a labyrinth where up could become down at any moment. Detecting these cosmic ghosts required more than telescopes. It demanded gravitational detective work. Using the Chandra X-ray Observatory, scientists spotted telltale flares from 2 locations where stars shouldn't have been active. These weren't stellar flares, but the death screams of gas clouds being shredded as they spiraled into black holes' event horizons. The third hole betrayed itself more subtly, by the way it bent the light of a distant star passing behind it, creating a double mirage, an effect only possible if 2 separate gravitational lenses, the first 2 holes, were joined by a third unseen distorting field. Together, they formed a gravitational hall of mirrors, twisting starlight into knots. What makes this trio so baffling is their improbable stability. Normally, black holes in such tight quarters would either collide or catapult one another into deep space within millennia. Yet simulations show these 3 have likely coexisted for millions of years, trapped in a delicate dance mediated by the system's 12 stars. Here's how it works. Whenever 2 holes drift too close, a passing star's gravity nudges them apart like a cosmic referee. The stars essentially act as living shock absorbers, their distributed mass preventing catastrophic mergers. It's a self-regulating system of celestial checks and balances unlike anything else observed. The most chilling revelation came from gravitational wave data. When LIGO analyzed subtle ripples from GQ 122, it found not the clean chirp of merging holes but a discordant hum. proof that all three were continuously warping spacetime as they orbited. Some frequencies matched theoretical predictions for triple orbits, where black holes move in nested figure eights. If confirmed, it would mark the first real-world evidence of such an unstable configuration somehow persisting long-term. Now the hunt is on to find how this trio formed. One theory suggests they're remnants of three separate galaxies' cores, merged long ago. Another posits they originated within the system itself, born from successive supernovae in a stellar game of musical chairs where the losers collapsed into darkness. Whatever their origin, their presence raises an eerie possibility. If black holes can hide in such numbers here, how many other, ordinary star systems might harbor hidden monsters in their midst? As instruments grow more sensitive, each new observation peels back another layer of this gravitational onion. And with every layer, we're forced to wonder, in a system where even light can't escape three competing abysses, what other cosmic riddles might be lurking just beyond our sight? Deep in the chaos of System HD 199999, a star refuses to die no matter how many times the universe tries to kill it. Meet V1234, nicknamed the Zombie by astronomers who have watched it cheat death not once but 3 times in the last million years. Most stars that go supernova vanish forever, their remains scattered across light years. But this cosmic survivalist has an ace up its sleeve, an orbit so erratic that it keeps getting flung out of harm's way at the last possible moment. The first near-death experience happened roughly 800,000 years ago when one of the system's massive blue giants exploded. Normally, the blast wave would have vaporized nearby stars, but V1234 was in the middle of a gravitational slingshot around 2 black holes at the time. The acceleration flung it clear just microseconds before the shock front arrived, leaving it singed but intact. Radioisotope traces in its outer layers tell the tale, an unnatural abundance of nickel-56, the telltale fingerprint of a supernova's fury that somehow didn't finish the job. Then came round 2. 500,000 years later, another neighboring star collapsed, this time forming a neutron star with a magnetic field so intense it began vaporizing nearby stars' atmospheres. Yet again, V1234's chaotic orbit saved it. As the deadly pulsar's radiation beam swept across the system, the zombie star happened to be tucked safely behind a dense cloud of debris, one it had coincidentally kicked up during a close encounter with a gas giant just decades earlier. But the most unbelievable escape came in 2022 when telescopes caught real-time footage of its third brush with oblivion. A hypernova, a supernova on steroids, erupted barely half a light year away, packing enough energy to sterilize planets across entire star systems. At the critical moment, V1234 was yanked into a sudden 90-degree turn by the combined gravity of 3 passing stars, narrowly avoiding the gamma-ray burst's kill zone. The Hubble Space Telescope later captured its outer layers glowing cherry red from the near miss, like metal pulled from a forge. What makes this star truly bizarre isn't just its luck, it's the physical toll these near-death experiences have taken. Spectroscopic analysis reveals a Frankenstein's monster of stellar compositions. Patches of young, hot hydrogen where it stole atmosphere from neighbors, mixed with ancient carbon deposits from its original formation, all laced with heavy metals from repeated supernova baptisms. Its core temperature fluctuates wildly, sometimes mimicking a young main sequence star, other times cooling to red giant levels as if it can't decide what stage of life it's actually in. Astrophysicists now suspect V1234's entire existence might depend on its impossible orbit. Unlike the predictable ellipses of most stars, its path resembles a drunkard's stumble through the system, influenced by every passing gravitational field. One month it might loop lazily around a quiet binary pair, the next it could be catapulted through the system's dangerous core at relativistic speeds. This constant chaos, while normally a death sentence for stars, has paradoxically become its lifeline, a celestial version of the old saying, "The only way out is through." The implications stretch far beyond one stubborn star. If zombie stars are more common than we thought, it could explain mysterious stellar populations that appear both ancient and youthful simultaneously. Some researchers even speculate that under the right conditions, a star like this might survive clear through to the heat death of the universe, hopping from one gravitational lifesaver to another in an endless cosmic game of survival. For now, V1234 continues its defiant dance, a flickering beacon in the chaos of its 12-star system. Every telescope pointed its way waits for the next act in this drama. Will it finally meet its match, or will the universe have to throw something even more extreme at this unkillable stellar phoenix? One thing's certain, in the cutthroat neighborhoods of duodecuple systems, sometimes the only way to live forever is to refuse to play by the rules. In the tangled web of a duodecuple star system, light doesn't just travel in straight lines, it ricochets between stellar surfaces like a cosmic pinball, creating optical illusions so convincing they've tricked even the most advanced telescopes. Picture this: a massive blue giant erupts in a flare, its light blazing outward. Instead of streaming into empty space, that light slams into the ultra-reflective atmosphere of a nearby superheated companion star, bouncing off at an angle that makes it appear to come from a completely different point in the sky. The result: ghostly duplicates, phantom flares, and stars that seem to blink in and out of existence depending on your vantage point. The most famous example is System K4722, where 3 stars orbit so closely they've essentially become a celestial hall of mirrors. In 2023, astronomers tracking a solar storm on the primary star watched in disbelief as identical flares appeared to erupt from 6 other locations, some separated by light days. At first, they assumed a catastrophic chain reaction was tearing through the system, but spectrographs told a different story. The flares were perfect echoes, delayed and distorted reflections bouncing between stars whose surfaces act like natural parabolic mirrors. One particularly dramatic reflection looped around 4 stars before reaching Earth, making a single event replay over 17 days like a cosmic greatest hits album. These aren't just visual curiosities, they're rewriting how we map such systems. In M338, what appeared to be a stable red dwarf orbiting peacefully at the system's edge was revealed to be an illusion when the star suddenly duplicated during an eclipse. The culprit, light from a hidden white dwarf, bent and magnified by 2 intermediate stars' gravity, projecting a flawless fake that persisted for centuries. Only when the aligning stars drifted apart did the mirage dissolve, leaving astronomers to recalculate the system's true population. The reflections create impossibly rare alignments too. System V9999 produces Einstein crosses, 4 perfect images of the same star arrayed in a cross, when its central black hole lenses light that's already been reflected by 3 other stars. It's like holding up a funhouse mirror to another funhouse mirror, creating recursive distortions that reveal otherwise invisible features. In 2024, one such cross exposed a previously unknown dust ring around a neutron star, visible only in the warped reflections. Perhaps the strangest effect occurs in System HD 12345, where reflections interfere with each other like overlapping sound waves. Light from a pulsar bounces off multiple stars, arriving at Earth in overlapping waves that sometimes cancel each other out entirely. For days at a time, the pulsar seems to vanish not because it's inactive, but because its reflected light is perfectly self-destructing in transit. It's the universe's most elaborate magic trick, proving that in these crowded stellar neighborhoods, seeing isn't just believing, it's deciphering a hall of mirrors where every reflection hides a deeper truth. What makes these illusions more than just cosmic curios is their potential to reveal the unseeable. By analyzing reflection angles and delays, astronomers can reconstruct the precise positions and atmospheres of stars too faint or distant to observe directly. Every distorted echo is a clue, and in the funhouse physics of 12 star systems, even light itself becomes a tool for uncovering secrets the universe never meant to show. In the heart of the system KX711, something impossible happens regularly. Stars change color right before astronomers' eyes. Not the slow, evolutionary shifts spanning millennia that we expect from aging stars, but dramatic, rapid transformations where a blue giant might flicker to deep red over mere decades, then revert just as suddenly. This cosmic chameleon act isn't due to any stellar metamorphosis. Instead, it's the ultimate parlor trick of overlapping atmospheres and gravitational lensing, where 12 stars conspire to bend light and perception into something unrecognizable. The key player is a pair of supergiants orbiting so closely their outer atmospheres physically touch, forming a shimmering bridge of plasma between them. The larger star burns a searing blue-white, its surface temperature exceeding 30,000 degrees Celsius. Its companion runs cooler at 18,000 degrees, glowing a fierce violet. Normally, their combined light would mix into a pale lavender hue, but add the gravitational influence of 10 other stars warping the path of every photon, and the rules of color physics get rewritten. When viewed from Earth's angle during certain alignments, the cooler star's light gets trapped in the hotter star's atmosphere, its violet wavelengths absorbed and re-emitted as brilliant cyan, a celestial dye job spanning millions of kilometers. The most jaw-dropping transformation occurred in 2022, when the entire system appeared to shift from blue dominance to ruby red for 18 months straight. Telescopes revealed the cause. 3 other stars had aligned in a perfect gravitational lens, magnifying and reddening the light of a normally faint red dwarf hidden behind them. The effect was so extreme that professional observatories recalibrated their instruments, convinced their filters were failing. Amateur astronomers in online forums first spotted the anomaly, noticing KX711 had vanished from its usual position in constellation maps, not because it moved, but because its color index no longer matched any catalogued entries. But the real magic happens during what astronomers call the prism events. Every 63 years, 5 stars align in such precise formation that their combined gravitational fields act like a cosmic dispersive prism. White light from the system's central star splits into a perfect spectral rainbow, with each color taking a slightly different path to Earth. For about 6 weeks, observers see not 1 star but 7. Each a different color of the visible spectrum, stretched across the sky like a stellar Newton's rings experiment. The effect is so precise that during the last event in 1959, scientists used the separated colors to measure interstellar dust concentrations with unprecedented accuracy. These chromatic gymnastics aren't just visual spectacle, they're rewriting how we interpret stellar data. For decades, astronomers assumed color indicated a star's temperature and age. Now, KX711 proves that in crowded systems, color can be a collective performance, orchestrated by hidden players. The system's red giant, for instance, isn't actually red at all. It's a yellow star whose light reddens as it passes through an orbiting disk of crystallized carbon, a substance created by colliding stellar winds that behaves like interstellar stained glass. Perhaps the most poetic revelation came last year when spectrographs detected impossible green hues in the system, a color stars physically can't emit under normal circumstances. The culprit, light from a blue star filtering through the electrically charged outer layers of a magnetar, shifting its wavelength to emerald through a process called cyclotron radiation. It's a reminder that in the chaos of 12 competing gravities and intersecting atmospheres, even the most fundamental laws of light can be bent sometimes into shades the universe wasn't supposed to show. Amidst the crowded chaos of a typical duodecuple star system, where stars jostle for position like commuters in a cosmic subway, one colossal outlier stands apart, literally. Meet the lonely giant, a monstrous star so massive it could swallow our sun 100 times over, yet mysteriously isolated in an otherwise densely packed stellar neighborhood. This isn't just unusual, it's like finding a solitary skyscraper in the middle of a bustling city block where every other building is tightly packed together. Located in the system HD 3209, this behemoth weighs in at roughly 130 solar masses, burning so fiercely it defies theoretical limits for stellar stability. Normally, stars this massive attract companions like moths to a flame, with smaller stars clustering around them in tight orbits. Yet this giant floats alone in a vast emptiness, its nearest neighbor a staggering half a light year away. Practically next door in galactic terms, but an eternity for stars used to brushing shoulders. The void around it forms a perfect sphere, as if some unseen force carved out a no-fly zone in the cosmos. Theories abound to explain this cosmic hermit. One camp argues the star might be an immigrant, a rogue giant captured by the system's gravity after being ejected from its birthplace elsewhere. But chemical analysis tells a different story. Its composition perfectly matches the other stars in HD 3209, suggesting it formed here. Another hypothesis proposes it once had companions, but its sheer ferocity vaporized them. Young massive stars emit ultraviolet radiation so intense it can strip away nearby protostars' gaseous envelopes before they fully form. Imagine a hurricane shredding clouds before they can become raindrops. This star might have literally blown away its would-be neighbors in its fiery youth. The most tantalizing clue came from radio telescopes, which detected faint, rippling arcs in the gas surrounding the lonely giant, echoes of ancient explosions. Some researchers speculate this star survived a brutal game of gravitational king of the hill, where competing stars collided or merged until only the heaviest remained. The empty zone around it could be the stellar equivalent of a cleared battlefield. Supporting this, simulations show that in dense systems, the most massive star often ends up sinking to the center through dynamical friction, scattering lighter stars outward in the process. But here's the twist. In HD 3209, the void isn't centered, it's off to one side like a displaced crater. This odd positioning led to a radical third theory. The lonely giant might be locked in an invisible tug of war with a hidden adversary. Recent gravitational wave data hints at a massive, dark companion, perhaps a black hole several hundred solar masses orbiting just beyond detection. If true, their gravitational dance could explain why the star seems to hover at the edge of nothingness, trapped between the pull of its unseen rival and the collective gravity of the system's other stars. Every few millennia, their close passes might slingshot smaller stars away like cosmic shrapnel, maintaining the giant's isolation. What makes this star truly mind-bending is how it reshapes our understanding of stellar nurseries. Traditionally, massive stars form in dense clusters where competition for gas is fierce. The lonely giant challenges that, proving under the right conditions, nature can build titans in relative solitude. Some astronomers now wonder if similar outliers exist in other systems, hidden giants lurking in artificially cleared zones, their origins lost to time. For now, the lonely giant remains an enigma, its empty neighborhood a silent testament to forces we're only beginning to comprehend. Whether it's a survivor of stellar warfare, a cosmic bully, or the prize in an unseen gravitational struggle, one thing's certain. In the crowded dance of 12 star systems, sometimes the most fascinating player is the one standing alone. Buried deep within the 12-star chaos of System L742, a cosmic jewel is slowly forming, one that defies everything we know about stellar evolution. Meet the diamond star, a carbon-rich anomaly that's not just twinkling like a gem. It's literally turning into one. This isn't poetic exaggeration. Spectroscopy reveals its core is cooling into a crystalline lattice of diamond-like carbon, a process that should take billions of years in isolation. But in the gravitational pressure cooker of its home system, time's being fast-forwarded in ways that leave physicists stunned. The star, catalogued as CR79, started life as an unremarkable mid-sized star about 2/3 the mass of our Sun. What made it extraordinary was its orbit, a precarious loop threading between three massive neighbors, each yanking on it like celestial blacksmiths hammering metal. Over eons, these gravitational tides stripped away its outer hydrogen layers, exposing a helium-rich core laced with carbon forged in earlier fusion cycles. Normally, such a star would quietly fade into a white dwarf over eons, but in L742, the relentless gravitational kneading from nearby stars altered the equation. Every close pass compressed its core further, squeezing carbon atoms into tighter alignments, while shockwaves from stellar collisions sent vibrations rippling through its structure, like tapping a glass to induce crystallization. Now, infrared scans reveal something unprecedented. The star's core has cooled to just under 3,000 degrees Celsius, crossing the threshold where carbon can arrange into a diamond-like structure. Not the tiny diamond flecks found in some white dwarfs. This is a singular, planet-sized crystal slowly growing at the star's heart. Simulations suggest that within 500,000 years, a blink in cosmic terms, the entire core could solidify into what's essentially the universe's largest gemstone, glowing faintly from residual heat and pressure-induced luminescence. What's truly bizarre is how quickly this happened. In isolation, crystallization like this would take tens of billions of years, longer than the current age of the universe. But L742's unique dynamics acted as a cosmic accelerant. The constant gravitational pumping from nearby stars keeps the core agitated enough to prevent full hardening while simultaneously driving the conditions perfect for orderly carbon alignment. It's like shaking a snow globe so precisely that the flakes arrange into perfect geometric patterns mid-fall. The diamond star isn't alone in its oddity. System surveys have spotted two other carbon-rich stars in Duodecuple systems showing similar premature cooling, though none as advanced. This suggests a previously unknown stellar evolution pathway, one where gravitational chaos doesn't just destroy, but sometimes forges cosmic masterpieces. Some theorists even speculate that such stars could be the universe's ultimate time capsules. If intelligent life ever stumbled upon a fully crystallized stellar core billions of years from now, its layered structure might preserve a readable record of the system's violent history, like growth rings in a tree but etched in atomic bonds. Yet the most poetic twist might be the star's eventual fate. When its 9 closest companions finally exhaust their fuel and collapse, their combined gravity could fling the diamond star clear of the system entirely. Imagine a stellar gemstone adrift in the interstellar void, cold and dark, waiting for some future civilization to discover the universe's most improbable heirloom, a diamond not forged in a moment of destruction, but in the persistent chaos of 12 stars dancing on the edge of eternity. In the labyrinth of stars that make up the Duodecuple system KX999, something impossible keeps happening, an eclipse with no apparent cause. Back in 2022, astronomers tracking the system noticed one of its brightest stars dimming by nearly 40% for exactly 3 hours and 17 minutes every 42 days. At first, they assumed a companion star was passing in front, blocking its light. But when they mapped all 12 stars' orbits, none lined up to create such a shadow. The dimming occurred anyway, like clockwork, as if an invisible hand were flicking a cosmic dimmer switch. The phenomenon, dubbed the phantom eclipse, follows precise rules that defy conventional explanations. The dimming isn't gradual, as with normal eclipses it's instantaneous, as if a curtain drops across the star's surface. Spectrographs revealed no dust clouds or planets in transit. Even stranger, the star's light doesn't just dim uniformly. Certain wavelengths vanish completely while others pass through unharmed, a filtering pattern unlike any known natural obstruction. It's as if whatever's causing this isn't just blocking light, it's editing it. theories range from the plausible to the extraordinary. One camp suggests an undetected disk of exotic matter, perhaps quark nuggets or Bose-Einstein condensates orbiting the star in a way that interacts with light uniquely. Others propose a gravitational anomaly where spacetime itself warps into a temporary lens that deflects specific photon energies away from Earth. The wildest hypothesis involves theoretical macrostructures, alien megaprojects designed to harvest stellar energy, though even proponents admit this is speculative at best. Then came the clincher. In 2024, the Very Large Telescope Array caught thermal echoes from the eclipse zone. Just before each dimming event, infrared sensors detected a fleeting heat signature, not from an object passing in front, but from empty space itself warming by a few degrees. It's as if whatever's causing the eclipse briefly emits energy before enacting its light-blocking effect, a behavior no known celestial body exhibits. The most tantalizing clue lies in the timing. The 42-day interval matches the orbital period of a hypothetical object calculations suggest should exist, a brown dwarf or small black hole that would explain gravitational wobbles in nearby stars. Yet every search for this missing body comes up empty. Some researchers now wonder if the eclipse maker isn't a single object, but a rotating knot of warped spacetime created by the overlapping gravity wells of multiple stars. A temporary knot in the cosmic fabric that tangles light rays passing through. For now, the phantom eclipse remains one of astronomy's most stubborn puzzles. Every new observation adds layers to the mystery, proving that even in the crowded chaos of 12 star systems, the universe still has tricks up its sleeve, ones that don't just challenge our models but seem to play by rules we haven't even written yet. In the cosmic orchestra of System MT711, the stars don't just orbit, they sing, not metaphorically, but in literal, detectable frequencies that resonate through space like celestial tuning forks. These aren't random vibrations, they're precise harmonic pulsations, rhythmic contractions and expansions of stellar surfaces that generate sound waves traveling deep into the star's cores and back out again. Normally, these oscillations are subtle, detectable only by sensitive instruments, but in the gravitational crucible of a duodecuple system, something extraordinary happens. The stars begin harmonizing, their individual notes amplifying into a chorus so powerful it warps the fabric of space around them. Take the primary star, VX9, whose pulsations should theoretically dampen over time like a fading drumbeat. Instead, observations reveal its oscillations growing stronger every decade, as if an unseen hand were turning up the volume. The reason: 5 neighboring stars orbit in perfect integer ratios to VX9's natural resonance, 3 completing 2 orbits for every one of its pulsations, 2 others matching its frequency exactly. Their combined gravity acts like a cosmic feedback loop, reinforcing the vibrations rather than suppressing them. The effect is so pronounced that in 2024, the LISA gravitational wave detector picked up microripples in spacetime correlating precisely with VX9's heartbeat, marking the first time stellar pulsations were detected through gravitational waves alone. But the real marvel is how these resonances cascade through the system. When VX9 pulses, its gravity tugs on a nearby binary pair, triggering sympathetic vibrations in their atmospheres. Those stars then nudge their neighbors, creating a chain reaction that ultimately reaches the system's outermost dwarf star, like a game of interstellar telephone played with seismic waves. The entire process takes 14 hours to complete, meaning the system isn't just singing, it's performing a meticulously timed round, with each star's entrance perfectly calculated by gravity's invisible baton. The most haunting music comes from the system's twin red giants, whose deep, slow pulsations produce frequencies equivalent to be flat 2 octaves below middle C, a note so low it vibrates at the threshold of human hearing. When these stars align with 3 rapidly spinning white dwarfs, their combined tones create a phenomenon astronomers call the Devil's Interval, a dissonant harmonic clash that, according to mathematical models, should destabilize nearby orbits. Yet somehow, the system has found equilibrium, channeling this acoustic chaos into a stabilizing force that prevents stellar collisions. It's as if the universe discovered its own form of destructive interference, where sound itself becomes the glue holding everything together. What's truly groundbreaking is what these pulsations reveal about stellar interiors. Just as geologists use earthquakes to map Earth's core, astroseismologists decode stellar vibrations to see inside stars. In MT711, the harmonics expose structures never before observed. Towering plasma geysers frozen mid-eruption by magnetic fields, spiral density waves wrapping around cores like cosmic fingerprints, and even hints of crystallized oxygen layers deep within one star's mantle, a phase of matter previously only theorized. Yet the ultimate mystery remains unanswered: why some duodecuple systems hum in harmony while others fall silent. Of the 30 known 12-star systems, only 6 exhibit coordinated pulsations and no 2 share the same song. Some researchers suspect it's a youthful trait, with older systems losing synchronization as stars age at different rates. Others argue it requires a specific cocktail of stellar types, like an ensemble where only certain instruments can resonate together. One daring theory proposes these systems are cosmic tuning forks left over from the early universe, their vibrations preserving a frequency signature of conditions long vanished. As telescopes grow more sensitive, we're not just observers of this stellar symphony, we're becoming audience members, listening as the universe unveils a hidden dimension where gravity composes and stars perform. And sometimes, if the alignment is just right, the music reaches across the light years, not as radio waves or visible light, but as the faintest trembling of spacetime itself, a reminder that even in chaos, there's rhythm waiting to be heard. Time doesn't flow evenly across the universe, not when gravity gets this extreme. In the heart of a duodecuple star system, where 12 massive objects warp spacetime into a tangled knot, clocks don't just tick slower. They stutter, stretch, and sometimes seem to stop altogether. Einstein predicted this over a century ago: the stronger the gravity, the more time drags. But what happens when you cram a dozen stars into a cosmic blender, their combined gravity twisting the fabric of reality? The results are so dramatic, they'd make even relativity's founder do a double take. Consider the system GRB 1199, home to 3 neutron stars orbiting a shared black hole. In 2023, the Chandra X-ray Observatory clocked time passing 42% slower on the surface of the innermost neutron star compared to Earth. That's not a tiny discrepancy. It means an astronaut aging 1 year there would return to find their Earth-bound twin nearly 2 years older, the culprit. The black hole's gravity, amplified by the neutron star's own dense masses, creates a gravitational well so deep that light itself struggles to climb out, stretching seconds into what feel like minutes. But the real shock came when researchers compared timing across the entire system. While the innermost star's clocks crawled, a red giant orbiting farther out ticked only 12% slower. Meanwhile, a rogue white dwarf darting between them experienced wild fluctuations. Its onboard atomic clock, theorized from spectral shifts, alternately sped up and slowed down depending on which massive neighbor it swung closest to. It's like watching a symphony where every instrument plays at a different tempo, yet somehow creates coherent music. The most mind-bending proof emerged from system PSRJ 0706, where pulsars act as nature's precision timekeepers. Their lighthouse-like beams should pulse at near-perfect intervals, but here the rhythm staggers unpredictably, not from stellar hiccups, but because the pulses we detect have fought through layers of warped spacetime. Some arrive early, having taken shortcuts through gravity wells. Others lag after looping around multiple stars like commuters stuck in cosmic traffic. By mapping these delays, astronomers reconstructed the system's hidden gravitational topography. revealing regions where time effectively stands still relative to Earth. This isn't just theoretical spectacle, it's reshaping space exploration. GPS satellites orbiting Earth already correct for our planet's mild time dilation. Future probes to multi-star systems will need far more radical adjustments. A navigation computer calculating a trajectory near GRB 1199's core could accumulate errors measuring in years if it ignored relativistic effects. Some engineers now simulate missions using gravity maps that treat time as a fluid, its flow rate changing block by block like neighborhoods in a celestial city. Perhaps the ultimate test of Einstein's theories lies in System K042, where two white dwarfs spiral toward collision. As they inch closer, their combined gravitational field intensifies, squeezing time like a cosmic accordion. Models predict that in their final hours before merging, clocks on their surfaces will tick half as fast as those on Earth, a phenomenon the upcoming LISA gravitational wave detector might soon observe directly. If confirmed, it would be the most extreme validation of time dilation ever recorded, proving that in the universe's most crowded stellar neighborhoods, time doesn't just bend. It shatters. The explosion should have been impossible, not one, but two stars detonating in perfect unison, their shockwaves colliding mid-blast like cosmic cymbals crashing together. In 2024, astronomers monitoring the Duodecuple system V970 spotted the telltale flicker of a supernova, then blinked in disbelief as a second flare erupted just 3.7 seconds later from a neighboring star. The odds of witnessing such a synchronized stellar death, roughly 1 in several hundred million, yet there it was unfolding in real time, a celestial spectacle that shouldn't exist but did. What made this twin detonation so scientifically priceless wasn't just the rarity, it was the forensic treasure trove hidden in the aftermath. Unlike solitary supernova that leave behind expanding bubbles of debris, these colliding shockwaves created intricate interference patterns, sculpting the ejected material into bizarre, lace-like structures. X-ray telescopes captured titanium and cobalt atoms, normally forged deep within a dying star's core, being violently stitched together in the overlapping blast zones, forming exotic isotopes never before observed in nature. The most startling, a fleeting radioactive chain resembling element 126, a super-heavy substance predicted by theorists but unstable under earthly conditions. For 17 glorious days, the supernova's maelstrom became a natural particle accelerator, smashing atomic nuclei together at energies rivaling the Large Hadron Collider. The explosions also acted as cosmic X-rays, revealing hidden structures within the system. As the blast light diffused through surrounding dust clouds, it illuminated previously invisible tendrils of gas twisted into double helix shapes, likely shaped by the system's complex magnetic fields. Even more intriguing were the shadows cast by two mystery objects that momentarily eclipsed the supernova's light. Follow-up observations confirmed these weren't planets or stars, but dense knots of dark matter, or something stranger floating between the system's surviving members. Perhaps the most humbling revelation came from timing the neutrino bursts. These ghostly particles, emitted milliseconds before the visible explosions, arrived at Earth's detectors with a perplexing delay between the two stars. Not because they traveled different distances, but because the second star's neutrinos had to climb out of an exceptionally deep gravitational well created by a nearby black hole. That tiny lag, measurable only with instruments like IceCube in Antarctica, provided the most precise calculation yet of the black hole's mass, 82 solar masses, give or take a feather's worth. Now, years later, the remnants continue to defy expectations. The expanding debris clouds haven't merged as predicted. Instead, they're engaged in a slow-motion ballet, their edges rippling with filaments of neon and magnesium that glow like celestial neon signs. Some filaments pulse rhythmically, driven by shock waves rebounding off unseen gravitational boundaries. Others twist into perfect Archimedean spirals, as if the explosions encoded mathematical blueprints in their fury. For astrophysicists, V970's twin supernova are more than a fireworks display. They're a once-in-an-era laboratory. Every unusual isotope, every distorted shock front, every lingering neutrino signature whispers secrets about how stars live, die, and sometimes against all cosmic odds, choose to bow out together in a blaze of synchronized glory. And somewhere in that tangled aftermath, there might even be clues to an even bigger mystery, whether such impossibly timed explosions could ever happen again. Or if we just witnessed the universe's most spectacular fluke. Somewhere between the organized chaos of binary stars and the teeming metropolises of globular clusters, there exists a cosmic missing link, a duodecuple star system so perfectly balanced between order and anarchy that it challenges where we draw the line between multiple star system and mini-cluster. Meet TF8801, a gravitational Rosetta Stone discovered in 2022 that's rewriting the textbook definitions of stellar groupings. At first glance, TF8801 looks like overkill, a dozen stars crammed into a space only slightly larger than our solar system's Kuiper belt. But zoom in, and the structure reveals an ingenious hierarchy that blurs the boundaries of known astrophysics. 6 of its stars form 3 tight binary pairs, each duo orbiting a shared center like miniature planetary systems. Those pairs then orbit another binary in a wider dance, creating a 4-tiered gravitational pyramid. The final 2 stars, they weave through this nested architecture like celestial free agents, their looping trajectories binding the entire system together without fully committing to any subgroup. What makes this system so extraordinary is how it mirrors the properties of much denser star clusters, just on a smaller scale. In globular clusters, stars are held together by the collective gravity of thousands. Here, 12 achieve similar stability through precision orbital engineering. The system's core stars orbit fast enough to generate the same velocity dispersion seen in clusters, a statistical spread in their movements that prevents collapse. While the outer stars act like cluster halos, their looser paths mimicking the behavior of stars at a cluster's edges. Even the distribution of stellar types matches cluster profiles, with ancient red giants coexisting with youthful blue stragglers in proportions otherwise only seen in conglomerates 100 times larger. The discovery has astronomers rethinking how star clusters might form. Traditional models assume clusters coalesce from massive, collapsing gas clouds. But TF8801 suggests another pathway. Small, intricate systems like this could be the seeds from which some clusters grow. Imagine dozens of similar 12-star systems drifting together over eons, their overlapping gravities merging into a single, denser structure. Supporting this, infrared surveys have spotted what might be TF8801's cousins, other mid-sized multiples with similar nested orbits, dotted throughout the galaxy's star-forming regions. The system's chemistry deepens the mystery. Spectroscopy reveals its stars share an unusually high concentration of europium and gold elements typically forged in neutron-star collisions. This suggests TF8801 might be the remnant core of a much larger group that lost members to past cataclysms. Perhaps it was once a 100-star cluster whittled down by supernova and gravitational ejections until only this stable skeleton remained. If true, it would mean what we're seeing is a cluster in its final, most efficient form, not a growing system but a distilled one. Yet the most tantalizing clue comes from what's missing. Despite its density, the system shows no signs of the stellar collisions or runaway mergers common in young clusters. Every star maintains a safe distance, their orbits fine-tuned to avoid catastrophe. It's as if nature hit upon the perfect recipe for packing stars together without sparking chaos, a recipe we've never witnessed anywhere else. Some theorists speculate this balance could only arise in systems with very specific mass ratios, where gravitational pushes and pulls cancel out almost magically. Others wonder if we're seeing the handiwork of a long-vanished black hole, whose past presence might have choreographed the stars into this improbable arrangement. As telescopes probe deeper into the galaxy's star-rich regions, the hunt is on for more of these transitional systems, the cosmic equivalents of Archaeopteryx fossils that blur the lines between categories. Each one found brings us closer to answering a fundamental question. Are star clusters just scaled up multiples, or do they represent something entirely different? TF8801 suggests the truth might lie somewhere in between, in a gravitational twilight zone where 12 stars can behave like 12,000, and where the universe's categorization schemes are waiting to be redrawn. At the heart of the Duodecuple system, ERA 0847, the universe has crafted an invisible masterpiece, delicate spirals of dust twisted into perfect concentric rings, shimmering only in the infrared spectrum like cosmic fingerprints. These aren't the dusty debris fields found around young stars, they're intricate, almost sculpted formations. They're particles aligned with such geometric precision that they resemble the grooves of a vinyl record spun across light years. The rings shouldn't exist at all, at least not in such perfect form. Normally, dust in multi-star systems gets blasted into chaotic, asymmetrical clouds by competing stellar winds. But here, 12 stars have somehow choreographed their gravitational pushes and pulls into a harmonious balance, creating stable, sweet spots where dust grains settle into breathtaking patterns. The innermost ring orbits so close to a binary pair that its particles should be vaporized, yet they endure, kept intact by opposing radiation pressures from 3 other stars positioned like celestial guardians. What makes these dust spirals truly bizarre is their chemical composition. Spectroscopy reveals crystalline silicates and graphite arranged in alternating bands, materials that usually require wildly different temperatures to form. Somehow, the system's overlapping heat zones create microenvironments where snowflakes of frozen carbon dioxide drift alongside scorching quartz like grains. The James Webb Space Telescope's mid-infrared camera captured this stark contrast in 2024, showing ice-laden outer rings transitioning abruptly to furnace-hot inner bands, all within a structure thinner than Earth's orbit around the Sun. Even stranger is how the rings move. Unlike Saturn's static bands, these dust spirals pulse rhythmically, expanding and contracting as different stars' gravitational tides dominate. Every 11 years, when 2 particular neutron stars align, their combined magnetic fields excite the dust into glowing like a neon sign, a phenomenon astronomers first mistook for a series of tiny supernovae. During these events, charged particles race along the rings at nearly light speed, creating temporary lightning that stitches intricate fractal patterns across the system, visible for weeks before fading into infrared invisibility once more. The most haunting detail, these rings might be cosmic gravestones. Radioisotope analysis suggests some dust grains contain traces of nickel-60, an isotope only forged in supernova explosions. The leading theory posits that multiple stars in this system perished catastrophically long ago, their remains ground into fine debris over eons. Now, their ashes dance in these precise formations, a memorial to stellar lives lost, sculpted by the very forces that once destroyed them. Yet for all their beauty, the rings serve a practical purpose too. The densest bands act like interstellar spiderwebs, capturing stray atoms and molecules that might otherwise escape the system. Over millennia, this collected material could birth new stars or planets, making these ghostly structures not just art, but the universe's most delicate nurseries. And somewhere in their shimmering contours, there might even be clues to how chaotic systems occasionally find moments of fleeting, impossible order. In the bustling stellar metropolis of System K1459, Astronomers expected to find aging stars winding down their lives only to stumble upon a cosmic nursery where new suns ignite in defiance of all expectations. Conventional wisdom says star formation is a young galaxy's game, with vast clouds of gas collapsing under gravity to birth fresh stellar generations. Once that gas is exhausted, the party's over, but K1459, a system estimated at over 5 billion years old, older than our solar system, should have been a retirement home for aging stars. Instead, infrared telescopes revealed something astonishing. Pockets of ionized hydrogen and glowing protostellar jets, the unmistakable signature of stars being born right now. The discovery sent theorists scrambling. How could a system this mature still have the raw materials to forge new stars? The answer lies in its chaotic gravitational economy. Normally, gas clouds need millions of years of undisturbed quiet to coalesce into stars. But here, the relentless gravitational tug of war between 12 massive bodies acts like a cosmic blender, churning old debris into new opportunities. When two stars pass dangerously close, their mutual gravity can shred ancient ice giants or strip the outer layers of red giants, releasing trapped hydrogen back into the system. Other times, colliding stellar winds compress stray gas into dense knots that ignite under pressure. It's stellar recycling on a grand scale, where death begets new life in a loop that defies traditional timelines. The most striking example orbits the system's central black hole, a protostar barely 100,000 years old, wrapped in a glowing cocoon of dust. Spectrographs show its composition is laced with heavy elements like iron and silicon, materials only forged in supernova. This baby star didn't form from pristine cosmic gas, but from the ashes of its predecessors, like a phoenix rising from stellar wreckage. Even more baffling is its growth rate. Fed by streams of gas siphoned from neighboring stars, it's accumulating mass 10 times faster than isolated protostars, potentially birthing a blue giant in a fraction of the usual time. Yet the real surprise came when researchers dated the system's other young stars. At least 4 showed similar late bloomer signatures, their outer layers rich in lithium, and element stars burn away in their first 100 million years. These weren't just recent births, they were evidence of an ongoing process, with new stars igniting every few 100 million years like clockwork. The implications rewrite our understanding of stellar life cycles. In the gravitational free-for-all of Duodecuple systems, star formation isn't a one-time event but a renewable resource, with each stellar death planting seeds for the next generation. What's unfolding here isn't just a scientific curiosity, it's a challenge to our cosmic timelines. If stars can form continuously in these chaotic environments, then our galaxy might harbor pockets of youth hidden among ancient stellar crowds. And if that's true, then somewhere out there, new worlds could be forming right now in places we once thought incapable of such magic, proving that in the universe's most crowded neighborhoods, the story of creation is far from over. Quantum physics teaches us that the subatomic world is ruled by uncertainty. Particles can be in multiple places at once or vanish and reappear unpredictably. But what if these bizarre quantum effects weren't just confined to atoms and photons? What if entire stars could exhibit quantum behavior? It sounds like science fiction, but a growing number of theoretical physicists argue that duodecuple star systems might be the universe's most staggering quantum laboratories, places where the rules of the tiny scale up to cosmic proportions. The idea first gained traction in 2021 when Dr. Alicia Chen's team at the Perimeter Institute noticed something peculiar while modeling the orbits of System L793. No matter how they adjusted their simulations, certain stellar paths couldn't be explained without invoking what looked like quantum tunneling, a phenomenon where particles teleport through energy barriers they shouldn't classically overcome. In this case, stars seem to shift between orbital states without traversing the space in between, as if executing celestial shortcuts. Skeptics dismissed it as gravitational slingshot effects gone haywire, but Chen's calculations suggested otherwise. The star's movements bore an eerie resemblance to quantum probability distributions, with positions that only made sense if you treated entire stars as wave functions rather than classical objects. Then came the real bombshell, System K904's entangled binaries. Two neutron stars in this 12-star arrangement exhibit spin rates that remain mysteriously synchronized across light years. When one suddenly slows, the other adjusts instantly, faster than light-speed communication should allow. The spooky correlation mirrors quantum entanglement, where linked particles react in unison regardless of distance. Mainstream astrophysics chalks this up to precession effects or hidden magnetic linkages, but a vocal minority, including Nobel laureate Dr. Rajiv Mehta, argues these could be genuine macroscopic quantum phenomena. If true, it would mean the universe has been hiding its most audacious quantum experiments not in lab chambers but in plain sight among the stars. The most controversial evidence emerged last year from gravitational wave data, when LIGO detected faint, high-frequency ripples from System V842. The signal contained what looked like interference patterns, peaks and troughs, suggesting multiple possible stellar configurations existing simultaneously before collapsing into one observable state. It's the hallmark of quantum superposition scaled up a trillion times. Critics counter that resonant harmonics between stars could mimic this effect, but proponents point to the timing. The interference cycles match theoretical predictions for a 12-body quantum system exactly. Of course, the big question remains: how could quantum coherence persist in such massive, noisy environments? A radical preprint from Caltech proposes these systems might exploit gravitational decoherence shielding. Just as Faraday cages block electromagnetic interference, the overlapping gravity wells of 12 stars could create a protected zone where quantum states resist environmental disruption. Others speculate dark matter filaments threading through these systems might mediate quantum connections, acting as cosmic waveguides for stellar-scale entanglement. While the debate rages, one thing's certain: if even a fraction of these quantum anomalies hold up, they'd rewrite physics as we know it. Suddenly, duodecuple systems wouldn't just be cosmic oddities. They'd be portals to a deeper layer of reality, where the line between quantum and classical doesn't just blur, it shatters entirely. And somewhere in their gravitational whirl, the universe might be running experiments far stranger than anything we've dared imagine. Buried deep in the constellation Cetus, a cosmic elder defies time itself. System HD1 99201, a duodecuple family of stars that's been spinning together for over 11 billion years. That's older than our Milky Way's thick disk, older than most globular clusters, and nearly as ancient as the universe itself. While other early star systems dissolved into the chaos of galactic evolution, this one endured, a gravitational heirloom preserved against all odds in the ever-changing cosmos. What makes this system's longevity so extraordinary isn't just its age, but the fact it survived the universe's most violent eras. When HD1 99201 first formed, the cosmos was a maelstrom of colliding dwarf galaxies and rampant star formation. Yet somehow, its 12 stars avoided being torn apart or flung into the void. The secret: a self-regulating orbital dance so finely tuned that astrophysicists compare it to a cosmic perpetual motion machine. Take its central quintet, 5 stars locked in a hierarchical orbit that resembles a Russian nesting doll. 2 tight binaries pirouette around a shared center, while a 5th star weaves between them at a precise resonance frequency. This arrangement creates gravitational sweet spots where perturbations cancel out, like a ship's gyroscope countering ocean waves. When one star drifts too close, the others nudge it back into place through a chain reaction of tidal forces. The result: not a single stellar collision in 11 billion years, a record that shatters theoretical predictions. But stability isn't this system's only marvel. Its stars are living fossils, their atmospheres laced with elements barely heavier than hydrogen chemical time capsules from an era before supernova enriched the cosmos with metals. The dimmest member, a red dwarf catalogued as HD 1-99201G, contains just 1/10,000th the iron of our Sun. Yet it burns steadily alongside younger, metal-rich siblings, proving multi-generational stars can coexist indefinitely under the right conditions. The most startling clue to the system's resilience came from Hubble data in 2023. Deep imaging revealed a faint, rippling halo of dark matter enveloping the stars, not the diffuse cloud typical of galaxies, but a precisely structured torus shaped by eons of gravitational interactions. Simulations suggest this invisible scaffold absorbs external shocks, protecting delicate orbital balances like a cosmic shock absorber. When dwarf galaxies collided nearby 2 billion years ago, or when rogue black holes passed dangerously close, this dark matter buffer likely prevented catastrophe. Yet for all its perfection, HD 1-99201 isn't frozen in time. Spectroscopic studies reveal subtle dramas playing out. One star, HD 1-99201b, shows bizarre isotopic ratios, its outer layers rich in lithium, an element usually destroyed in stellar cores. The likely explanation: it recently cannibalized a younger, lithium-rich brown dwarf that strayed too close, proving even this ancient system still evolves. Another star pulses irregularly, its vibrations suggesting a crystallizing core, a diamond the size of Earth slowly forming at its heart. Astronomers now view this system as a Rosetta Stone for stellar longevity. Its survival blueprint, hierarchical orbits, resonant frequencies, and dark matter stabilization might explain other ancient multiples glimpsed at the universe's edge. Some even speculate its stars could outlive the Milky Way, persisting into the era of proton decay when most celestial objects have faded to dust. As new telescopes like the 30-meter telescope come online, HD 1-99201's secrets will keep unraveling. Every flicker of its stars, every tremor in its dark matter halo, tells a story written across cosmic epochs, and in that story lies a humbling truth that against the backdrop of an ever-changing universe, some structures find a way to endure, not through luck, but through the delicate balance of forces we're only beginning to understand. From reckless hypervelocity stars to ancient celestial time capsules, from quantum-entangled binaries to stellar zombies that refuse to die, our journey through 30 of the strangest Duodecuple star system discoveries has been nothing short of cosmic whiplash. These aren't just quirks of the universe, they're full-scale revolutions packaged in starlight, each one tearing up our playbook on how gravity, time, and matter behave under extreme conditions. Think about it, we've witnessed systems where stars act like synchronized swimmers in a gravitational ballet, where invisible black holes puppeteer orbits like cosmic marionettes, and where entire planets surf between 12 suns on rails of pure chaos. If there's one lesson screaming through all this madness, it's that the universe doesn't just tolerate complexity, it revels in it. These discoveries aren't just trivia, they're seismic shifts for astrophysics. The existence of stable 12-star systems forces us to scrap old assumptions about orbital mechanics. Time dilation effects measured across these stellar metropolises are putting Einstein's theories through stress tests we never imagined possible. And those eerie, synchronized pulsations, they're hinting that stars might communicate through vibrations we're only beginning to decode. Even our search for life gets a shake-up. If planets can survive and even thrive in these gravitational mosh pits, then habitable zones might be far more flexible than we ever dreamed. But here's the exhilarating part, we've barely scratched the surface. Every answered question births 10 new mysteries. What lurks in the gaps where our math says mass should be, but our telescopes see nothing? Are those perfectly harmonic star systems natural masterpieces, or could there be forces at work we haven't even named yet? And let's not forget the granddaddy of all questions. If duodecuple systems can bend the rules this dramatically, what other celestial rebels are out there, rewriting physics in corners of the cosmos we haven't even glimpsed? So now it's your turn. Which of these 30 discoveries left your jaw on the floor? Was it the diamond star crystallizing in fast forward, the phantom eclipses defying explanation, or the ancient system older than the Milky Way itself? Drop your favorites in the comments, and while you're there, tell me what cosmic mysteries we should tackle next. Because if this journey has proven anything, it's that the universe's imagination dwarfs our own, and the next mind-blowing revelation might be just one observation away. Until then, keep looking up. The stars aren't just points of light, they're chaos, poetry, and infinite questions all rolled into one.